yeah, at the moment, I've got AI in my job title, as you can see. So I feel I'm sort of moderately qualified to tell you a little bit about it. But I will start, try and start at the beginning and lead you through it as a journey, and then we'll see where AI pops up. Yeah, so that's gonna happen. Come on, yay! So I started my university education in Oxford. Sorry if you think that's a little bit elitist, but there you go. I was very glad of its high standards, and I was actually 16 when I started my degree, so I have a lot of fellow feeling for Jui. I know what it's like to be kind of the bright, precocious youngster who knows everything, although she's considerably braver than me because she's going and telling all these grown-ups everything she knows. I wouldn't dream of doing that at her age, although I do now. So the Oxford engineering degree is quite a broad degree that covers a lot of engineering disciplines, from fluid dynamics to information technology, and I specialized in computer science, and we did in fact cover neural networks in one of our later modules, taught by a guy who's now a professor and head of department, head of everything. So we were very lucky there. But as you can probably guess, the proportion of girls in my year, 15% at a stretch. So from a very early point and pretty much all the way through, I was in a very small minority and had to learn to, you know, cope with it one way or another. So after I finished my degree, I spent a very long time working in the broadcast industry, broadcast technology, in a variety of roles spanning both development, software development. So I did, you can see down the bottom here, I started out programming in Pascal and moved on to Java and C++. These days it's mostly Python that I code in for the AI stuff. But back then I did also a lot of research for image processing. So I have always worked with images of one kind or another. So on the top left here, you've got an example of a test chart, in fact, a test video that we developed for the launch of digital terrestrial broadcasting in the UK. So the first digital television in the UK, before they started broadcasting it, they needed to know whether it was going to work, whether all the new kinds of smart tellies that people were buying were going to work. And they didn't have anything to test it with because they haven't started broadcasting yet. So it was a bit chicken and egg. So we produced these test streams that were guaranteed to be done right according to all the new standards. And that was one of the things that I developed. I was involved in quite a lot of research for doing things like motion estimation and compression, which are also needed for the new digital broadcasting. So I did learn quite a lot about how to squish pictures into smaller files is essentially what it comes down to. And I spent probably, now let me think, nearly 15 years working in industry as either a researcher or a developer on this broadcast stuff. And then a point came where I'd had enough and realized that the ultimate purpose of the broadcast industry as an industry, what they're driving for is to have more people sitting on sofas for longer periods of time watching something with adverts in. That's really what makes money, and ultimately is kind of the purpose of the whole thing. You hope public service broadcasting also provides educational enlightenment, but that's a rather small part of it. And I really wanted to do something bigger and better with my life. I realized, you know, that I had the talents and I wanted to learn something new. And the company that I worked for was a family company, so I couldn't very well go off and work for the competition. So my solution was to go and do a doctorate in computer vision. So I was very lucky. I found a lab at the University of Surrey, which is not very far from where I live, because at the time I had 2 children in primary school, so I couldn't up sticks and go to the other end of the world just for a doctorate. A lab called the Centre for Vision, Speech and Signal Processing. It is quite a large AI and machine vision lab, and I was very lucky to be supervised by the professor who's head and founder of this laboratory. And the work I did was mostly on medical images, and again that was a very conscious choice and wish of doing something that was contributing something meaningful to society, really. So there were 2 types of images that I worked on. The ones on the right are they're both microscopic images. I love microscopes because it's the sort of magic of seeing the invisible. So the ones on the right are kind of very thin slices of, in this case, cancerous tissue. And what you're looking for, I don't know if you can you see the little yellow circles? Some of the things have got little yellow circles for them. So there's lots of different cells, and some of them are dividing. And obviously the more of them are dividing, the quicker that tumor is growing. So the grading of cancer aggressiveness is based in part on counting how many of the cells are dividing, and it's quite difficult to identify which ones are dividing. They don't look that different from the others, and they can look in lots of different ways at different stages of the process. They look different, and you have to find them all. So it's quite a challenging task. It takes pathologists 6 years or something to train to do this by hand, as it were. But that's one of the topics that is increasingly being automated successfully with AI methods, including most successfully convolutional neural networks that Jui will tell you about a bit later. And the other kind of images, the green ones, are fluorescent images where a special dye that glows at a special wavelength is used to, again, color some cells, and the different patterns of green, so whether you've got little speckledy dots, whether you've got bigger blobs, whether how lumpy or smooth it is, that tells you about different types of autoimmune disease. So these are used to identify autoimmune disease. So those are the kind of two big projects that I worked on during my PhD, and I started in 2010, and in 2013, when I was nearly finishing, all these amazing results started coming out from deep learning, deep convolutional networks that were beating everybody, including me, in every competition. And yeah, they were just ahead of the field, but it was a bit too late in the day for me to, at that point, turn around and do my PhD all over again using the different new methods. So unfortunately, I didn't get to play with that during my PhD, but I have caught up since, I promise you. And I'm the biggest advocate of deep learning there is now. I go and do talks to management types about why deep learning is better than any other kind of machine learning. So that's really my kind of discovery of AI and how I came into it. And one of the interesting reflections for me was how different I found it to my expectations. So I thought, well, this is going to be easy. I know how to code, done that for 15 years. I've worked with images all of my working life. I know how all of that works, filtering, whatever, you know, I've done it. Algorithms, detections, yeah. Turned out that machine learning is all stats. And stats was not my favorite subject. I had to learn an awful lot of stats. So that was a little surprise for me. But hey, I now respect stats, and actually the biggest lesson I learned was from the stats to value diversity. I came from a programmer's background where, and we'll touch on this in a second. In fact, is that, yeah, that's the next slide. I came from a software developer background where you give it a series of instructions. You know exactly what you want to happen. And what you don't want is variation. And what you want in machine learning is the opposite. You want as much variety and diversity as possible, so that you learn to cope with all of those different things happening. And I think that's a very important principle to understand, the difference between your ordinary software development, programming of any kind, and machine learning. Unfortunately, when I tried to Google some clip art for software developer, this is what I got. And I was really not very happy with that. So I had to replace it with the rather happier lady there. So I'm not sure whether Jui has explained this in a previous workshop, but I will reiterate, if I may. So the difference between programming and machine learning is that you don't tell it what to do. You don't tell it what the steps are. You know, in a traditional algorithm, you might say you've got to square this and multiply it by 5, and then you got to add the other thing and, you know, put it through some other function. You don't need to do that. And when you try and do that, you as human with your limited understanding of the rich, diverse data, get it wrong. So in machine learning, you say, these are the right answers for all the diverse examples that I could find. you figure out what it is that needs squaring and multiplying by how much and combining with what else. And it is through the computational capability that's available to us now, as well as the mathematical understanding that has been built up over the decades, that we can, the combination of the two is what allows us to just throw the data, there's a little bit more to it, at the robot and let it figure out how to do it best. And the results, often than not, are much better than humans trying to interfere in the process. And it's, you know, if you think you know better, the chances are you don't. So I'll tell you a little bit about what I do now that I am back in industry. So I work for a company called Untitled for a division that is involved in traffic safety. So we make speed cameras, is what that means. So these yellow guys up above a road is what we make, and I'm in charge of putting the clever neural network that goes inside its head and is able to turn the pixels in the photograph of the number plate into the numbers and letters that are shown on it, number one, or take the photograph of the vehicle as a whole and say things like, what color is it? Is it a car? Is it a lorry? Different speed limit will apply to it if it's a lorry or a van. It's not allowed to go as fast. And again, we have to work really hard to make this work in real world diverse scenarios. We have to make it work whatever color that vehicle is, whatever side you're looking at it from, whether it's night or day, whether that number plate is from Texas or from Belgium, whether it is covered in snow and muck, whether it's half covered up by a bicycle. So the interesting part for me is making the AI work in the real world. That's the hard bit, the challenging bit. You know, you can read academic publications and they will typically be on, initially at least, when they're starting on a particular area, on carefully curated, selected data sets. And when you throw it in the real world, the results are not nearly as good. So for me, that's the interesting bit. And I think I will just show you one more example that I've been involved in a different division of our company that's involved with industrial inspection. So these are manufacturing plants, for example, making cars, aeroplanes, whatever, and they have large quantities of parts of some kind whizzing along a production line, and you need to spot when they've gone bad. So if you take an image of this screw head and it's a good one, when it comes through the what's called autoencoder that knows what they're supposed to look like, comes out all nice and evenly blue. And if there's some kind of damage on it, then it spots, you can see the sort of big red angry blotches where the damage is, and it doesn't fit what the part normally looks like, but it's not looking for a particular type of damage. It's not programmed, it's not shown in advance what damaged things look like. It's only shown what the good things are supposed to look like. So if the damage is a bit different in different places of a different kind, it still finds them just because they don't fit normality. So that's sometimes called anomaly detection or abnormality detection. And the same kind of methods get applied in lots of different visual fields. This is just an example that happens to be in industrial inspection. And the point is that the more you can automate these kind of things, the more the people can sit back and relax and go and do something more interesting than inspecting screws on a production line. It's really the kind of the purpose of the automation. So that's really kind of my whiz through the things that I do. I'd just like to conclude with an observation that as an employer who hires researchers, graduates, interns, etc., I can observe a massive skills gap, and nobody will argue with me that the skills gap in AI is huge. We'll also hear about the shortage of women in technology in general and the gender pay gap. So for me, the solution is kind of obvious. You know, the reason women on average are paid less is that they're doing the kind of jobs that are paid less. These are well-paid jobs because there's a skills gap. People pay a premium for anyone who knows this stuff. And the more girls can do it, the more we will close both the pay gap and the skills gap. And one of the things I've done recently, but Georgina's also been involved in similar things, is a program called Code First Girls that teaches quite introductory. So I taught a Python course, an introductory programming course for young women who do not have a technology degree or technology education, but are considering switching into technology fields. And it was a really, really rewarding experience for me. I cannot applaud them enough. And working with these groups of young women, they were inspirational, and my fellow instructors were fantastic to learn from. And I can just say, bring it on. And for some reason, they were really, really keen on emojis and Party Blob. So I leave you with Party Blob.
So a quick question from Kathy. What about older women that would like to learn? What advice have you got for them, Violet?
My advice for any older person who would like to learn is always, it's never too late. I do not believe that it's too late to learn for anybody. So I think that the system is unfortunately constructed in a really biased way. You know, you can get a student loan if you're 20 but not if you're 50. So that seems wrong. I found it fantastic to do a doctorate as a mature student. People worry about going back to school. Yes, it's hard, it's challenging, but actually I knew what I was doing it for, why I was doing it. There are so many people who go through onto masters and doctorates just by default because they've done well academically and they don't know what to do with their life. And that's a terrible, terrible waste. And it's equally a waste for a first degree. So many youngsters feel compelled to go to uni because if they don't, their life will end. And that's just wrong. And I promote at every opportunity schemes with industry placements. There's a great year in industry scheme that puts students into industry before they start their degree. They are the best students. They understand from the beginning of their studies why they're studying this subject, what they want to learn, so they want to learn, and they do so much better. So whatever your age, you have massive advantages from experience in general of workplace, of life. There is no reason not to learn new technical skills that in combination with existing skills will propel you. You know, I joined my current company as a lowly research engineer, and within a year I was head of AI, hiring my own team, because I already had experience of working in industry for a decade and a half. If I'd been a straight through school kind of doctorate, it just wouldn't be possible.
Does that answer your question, Kathy? You're on mute, but you're not.
Yes, it does. It does.
Wonderful. Thank you for asking that. And then I thank you for contributing. Next time in December, we've actually got an AI company who's going to bring their head of recruitment and tell us what they look for when they hire as well. So that'll be fun, in addition to what Violet's just said. Violet, thank you very, very, very much for that impassioned talk, both about your work.
How do where is it? There's got to be a stop button on it somewhere.
What are you looking to stop?
Oh, I'm just the screen share. Have you done it?
I've done it for you already.
Okay, thank you.
My pleasure. And so please do join me if you just put a quick note in the chat just to say thank you as well, if you would, to Violet for spending her time with us tonight. She does keep a pretty busy schedule, as you can imagine, with her type of work. Thank you, Bridget. So Jui, let's move across and let's spotlight you and your wonderful background. So Jui, this is the time that I hand over to you now to lead this session. I'll be on the chat for anybody who needs to ask questions or check with me or technical stuff or anything you want, but otherwise you're in Jui's very wonderful, capable hands. It's great to have you here again.
Sounds good. Let's get started. Can everyone see my screen?
You can.
Okay. Yeah, so as I said earlier, in this workshop, we're basically going to be learning about the basics of computer vision. So kind of like how Violet is able to use computer vision to detect license plates in her daily job, we are going to see how exactly that works and how we can apply it to different uses as well. So in this workshop, it's basically a beginner-friendly workshop, so we'll start with an introduction to AI, which is artificial intelligence and machine learning. And then we'll move on to a high-level overview of convolutional neural networks, no math. And then we will also create our own CNNs without coding at first. So we'll be using something that Google has made where they basically take care of all the coding for you, but you still need to be able to understand the theory. And then we'll also be creating our own convolutional neural networks with code. So yeah. And if you have any questions at any point, you can put them in the chat. I can see the chat. And you can also put them in, or you can like raise your hand or unmute your mic. So first, let's start with AI and machine learning. So what is AI? AI is basically when a computer is able to perform tasks that normally require human intelligence. And this can include vision, speech recognition, and language processing, so like Siri. It can also include robotics. Can anybody else give any examples of what you may think AI is?
We spoke about it being the Netflix and the Amazons, being able to turn Amazon.
Recommendation engines.
Yes.
Definitely.
And prediction engines as well.
And also things as simple as like rule-based chatbots would be considered AI because they're technically performing a human task by conversing with you. So AI can be super complex, like machine learning, but it can also be really simple, like a couple of if-then statements.
Well, what about some of your websites? Especially now, you know, most of us or all of us, anyone is on a computer now, and you have a lot of interaction with a computer. You know, you're not just out here doing face-to-face, but you're on a computer now. I mean, even with this is kind of an AI experience because you're able to see different people and able to have courses online. I would kind of consider this kind of an AI experience, as well as some websites where you're maybe ordering things or you're learning about certain things. You're getting some kind of feedback from the website and its server. I kind of feel that's an AI experience too.
Yeah, that's a really good point. Like maybe like virtual teachers and stuff, or like shopping.
Mm-hmm.
Yeah.
Yes.
I can throw in the dictionary definition for you, which is what I normally start with. So intelligence is essentially capacity to learn. So Kathy said learning several times there. So that's the critical bit, is does it learn? Learning is defined as improving the ability to perform some kind of task from experience. And in the case of computers, that experience is generally encoded as data. So data stands in for the experience that we as humans will have either by reading or listening or doing something to the computer. That comes in the form of data. And as long as it can improve its ability to do something, it's learned, then it's being intelligent.
Yeah. So we'll also be talking about machine learning, which is a subset of artificial intelligence, where, like Violet said, basically it's the ability of a machine to learn or improve from looking at a bunch of data. And it looks at patterns in these data. So it looks at patterns in this data, and it changes this mathematical algorithm based on exactly what you want the computer to do. So for example, you don't code what you want the computer to do, you just show it a bunch of data and it'll change its algorithm to learn from the data and perform the task that you want it to do. So that definition, if it didn't make a lot of sense, that's totally fine because we're going to break it down. So first of all, what is an algorithm? Does anybody have like an example or something that you want to share?
Is it like a if this then that type of thing?
Sorry?
Is it like an if this then that?
Oh, yeah, definitely. That is an example of an algorithm. An example that I like to work out with, if we were in person, we would have done this, is like, suppose you want to make a paper airplane. So pretend you like take your paper out and then there's directions. So first I'm going to say fold like the right half of the paper in like a triangle, and then fold the left half in like a triangle, and then fold it in half, and then fold the wings back. So that list of steps was basically an algorithm. So basically an algorithm is anything that is a list of steps that creates an output. So similarly, an algorithm for, say, machine learning is a list of steps that the machine has to follow to create an output. But these algorithms in machine learning are basically mathematical equations, and machines are able to learn by changing the values of this mathematical equation in order to make the output as accurate as possible. So that's basically how an algorithm learns. It basically changes the values in this equation to make the output as accurate as possible. And it does this by taking in a lot of data. So this data is divided into a training set, which is what is on the slide right now. It's where the data is labeled. So you know that if you're trying to classify between apples and oranges, and you see a bunch of pictures of apples and oranges, In the training set, you know that a picture of an apple is an apple and a picture of an orange is an orange. The machine will know that. So the model will create the mathematical equation, also known as the model or the algorithm, to predict the proper labels. So when it sees a picture of an apple, while it's training, it will try to see if it can predict that it accurately is an apple. And it will try to minimize the error. So the error is the difference between the actual labels and the labels that the model predicted. So if the model predicts that an apple is actually an orange, then that will increase the error. But if the apple correctly predicts that the apple is an apple, then it will decrease the error. So that is basically how a model learns from the training data. And then there's also a testing set. So in the testing set, the model doesn't know what the labels of the data are, and its job is to try to predict them. And in the testing set, we're able to find out as machine learning engineers how well the model actually learned. So this is where the model looks at a bunch of data and it classifies all the data, and then you can look at different performance metrics like accuracy, specificity, or sensitivity to see how well your model actually learned from the training set and how well it performs on data that it's never been seen or never seen before. So in summary, the model can learn from the data in a training set, and it will find patterns in this data, and it will change its mathematical equation that represents the model to predict the correct outputs, and then you can test it on the test set. So to drive the point home with an example, this is the difference between a training set and a test set. If you were trying to create a model that recognizes handwriting, you would first divide your data into a training set and a test set, and then in your training set, you would basically feed in images of handwritten numbers, and you would give the computer a label. So for example, this 5 would be given the label of a 5, and so on. And then the computer would train on those images, and it will come out with a mathematical model that when it gets a picture of a 5, the output will be the number 5. And then once your model is all trained, then you will test it on images it's never seen before. So you can test it on like a handwritten 9, and it should predict a 9 if it has trained properly on the data that it was supposed to train on. So now you may be wondering, how do you know when the model is done training? Like, how do you know when the error is minimized? So there's this thing called stochastic gradient descent, which is basically a really fancy word for saying how to minimize error. So if you think of the error in your model as a big curve like this, can everyone see my mouse?
Yes.
Okay. So suppose, well, as you all know, when the machine first starts learning, it has an equation, right? So before it's seen any data, the values of this equation, like suppose the equation was y equals x squared, and that's the equation that you're going to use to predict outputs. So suppose that equation, before you start learning, the numbers in that equation are random because the machine learning model doesn't know what the data looks like yet. It's never seen it. So at that point, when they're random, the error is going to be pretty high because this is the error curve. So numbers that are higher on the curve, it's going to be higher error. So it's going to be over here. And then the job of the model is to move slowly down this curve until it gets to the lowest error over here. And how it does that is it changes the values in the equation. So it'll change, suppose if it's y equals x squared, it might change from a coefficient of 1 to maybe y equals 2x squared or y equals 3x squared, and so on. And then as it changes the equation, you can see the error going up or down. And then, yeah, so basically that's how the error changes. And there's this thing called learning rate, which dictates how fast the model changes its weights or its coefficients or whatever you want to call it. So a big learning rate will have the model jumping around. So going back to the earlier example, if your model was y equals x squared, but you had a really large learning rate, so after y equals x squared, it would go to like y equals 5,000 x squared. And that would drastically change your error, and you might skip over the minimum error. So that is a drawback of the big learning rate. So basically, that's why like as you can see, big learning rate would be fast, but it would also skip over the smallest error. Then you can also use a smaller learning rate to minimize your error. And the problem with this is it goes really slow, but it'll usually make it to the bottom of the curve to minimize error. So in summary, error is minimized using this thing called stochastic gradient descent, which is a really fancy word for basically saying you have an error curve and you want to make it to the bottom of the curve. How you do that, you have two options. You either have a really big learning rate where you jump around and you might make it to the bottom, but you might even skip it. Or you have a really small learning rate where it'll take you a long time, but you'll probably make it to a pretty low point on the curve. And the lowest point on the curve is the lowest error. So does that make sense to everyone?
It does. Could you give me an example of when I would choose to use one over another? Are there examples in real life that we might be familiar with, where we know which one you might have they might have chosen?
Yeah, so I mean, I'd also like Violet's input on this, but I'm thinking many times, especially when you value accuracy, you would want to go with a smaller learning rate. So for example, if you're doing like the cancer example, or if you're doing the license plate example, I would go with a smaller learning rate because yes, it would take more computational power and more time to train the model, but in the end, the model will be better at detecting license plates or detecting cancer growth rates.
Yeah, it's not quite how it works. So sometimes if you choose a small learning rate, you never get there. It's the analogy I like to use is about trying to find the top of a mountain. Imagine you're trying to get to the top of a mountain. Find where the top is, the highest point, the one with the best performance. You don't have a map. You're standing there in fog. You can't see where the higher points are. All you can see is the ground under your feet and which way it's sloping. And this is the gradient descent bit. So you can see which way the ground's sloping where you are now. So you know the ground is rising that way. So you want to make a step in that direction rather than the other way. But you don't know how big a step to make. If you make tiny little steps, you might not only be there forever, but you might go round a little hill in the foothills and never find the really big mountain that's a kilometer away. On the other hand, if you make a step that's too big in the fog, not knowing where you're going to land at the end of your step, you might suddenly step off a cliff and drop down to a precipice. If you make your learning rate too big, you might jump over the mountain to the other side and miss it altogether, which is what Jui was describing. So in practice, you have to try it and see. For your particular problem, you try out different sizes of learning rate. And in fact, there's a little bit more to it. You have to sometimes have what's called a learning rate schedule, where you start off big, you get roughly in the right vicinity, and then you make your steps smaller as you try and find closer to the peakiest bit of the peak. So it's a black art is the answer.
Right. And I guess the more important the accuracy and the lower the error is, the more your experience in the black art comes into play.
Or the more you burn server time in just trying out lots more combinations.
Okay, thank you.
The learning rate is something you control, and that's why it's like kind of like guess and check, I guess.
Cool.
So now that we have the basic gist of how machine learning works, how error is minimized, and how you know when a machine has learned, let's talk about a specific type of machine learning, which is called deep learning, which is basically the entire field of like neural networks, convolutional neural networks, and so on. And we'll be focusing in on a special type of neural network called a convolutional neural network, which is commonly used for classifying images. So while we're going through learning about convolutional neural networks, there are a couple big ideas that we should keep in our minds that will kind of like anchor us as we like learn new information. So the first idea that you should remember, if you're ever in doubt, is that the neural network is modeled after the human brain, and thus it's made up of a bunch of neurons. And if you can kind of like intuitively think about how our brain works and how our brain learns, then that's kind of intuitively how a neural network learns. So going back to the idea of the human brain, this is what a human neuron looks like. And this is like vocabulary that, I mean, you can memorize if you want to, but it's like not really relevant to this, but it's just like a nice analogy to look at. So basically in the human neuron, there's a bunch of these interconnected neurons that when they're like, there's a bunch of interconnected neurons. So when you get an input or like a stimulus or something, it is taken in by the dendrites. And the dendrites can be either connected to sensory centers like your eyes, your nose, your tongue or stuff, or it can be connected to other neurons. And so the dendrites take in your inputs, and then the processing of this new information happens in the soma or the cell body. And then this new information is pushed out through the axon to other neurons, where the neuron itself chooses whether to fire or pass on the information or not fire and don't pass on the information. So that's how a neuron works. It's basically the brain works. It's basically a bunch of neurons that are deciding whether to fire or not to fire. And if a lot of them fire, then the signal passes along to wherever its destination is. So for example, if I accidentally touch like a burning pan, then the input would be like heat, and a bunch of neurons along the line, I'm not a biologist, along the line from my finger to my brain would like fire, and I would be alerted in my brain that I have touched something hot, and then I would move it. So that's how like neurons work in the brain. So similarly, in a neural network, neurons are structured really similarly. So they take in inputs, which you can see over here, and the processing of the data, which was taken from the inputs, happens in the cell body, and the neuron decides whether to fire or not using this activation function. Fire or not, like there's different definitions, but like if you're looking at the biology definition, like the activation function would decide whether the neuron fires or not, and then you would go to the corresponding output based on what the value of your activation function was. So in a neural network, there's a bunch of these neurons all interconnected, and they help process the data in the network, and they help the network learn. So the second big idea is that images are perceived as a set of pixels by the machine learning algorithm. And so we see images as, I don't know, like color, but computers see them as numbers. So for example, this is a picture of Abraham Lincoln. And we see something over here on the left, but in like better quality, I would say. But that's basically what we see. We just see a bunch of these colored dots, and then when we zoom out, it looks like a picture of Abraham Lincoln to us. But each of these colored dots represents a pixel value. So for example, this one in the top left represents 157. And the computer doesn't see the colors, it just sees the numbers that correspond to the colors. So what we see as a picture of Abraham Lincoln, the computer sees as a nice rectangle of lots of numbers. So that's basically how computers see images, and this will be really important when we're learning about how the data processing or the learning actually happens with images. So the third big idea is that images have certain spatial relationships which must be preserved in order for the machine learning model to be accurate. So for example, in Abraham Lincoln's face, for example, the eyes have to be a certain distance away from the nose and from the forehead in order for that to be an image of Abraham Lincoln. And if you're looking at an image of me, it's a different distance. So these spatial relationships are often destroyed when you're looking at regular neural networks, and that's why it's necessary to use convolutional layers and convolutional neural networks. So can anybody tell me the difference between the left, which is a regular neural network, and the right, which is a convolutional neural network?
Diamond,
The number of nodes are decreasing, like the inputs from layer to layer.
Yeah, but I guess that's kind of happening in both of them, right?
I think Richard might have it. Are you on mute, Richard? He's put in the chat, he's saying, is it 3D?
I was wondering, you've got depth on the right there.
Yeah, you do. So in the convolutional neural network, like I said, it takes into account spatial relationships as well. So in a way, it's kind of 3D, whereas in a regular neural network, it's just 2D. So this is a high-level overview of the structure of a convolutional neural network. And as you can see, it basically takes in an image. The image goes through a bunch of different layers. These are the names of the layers over here. And it learns the patterns of the image and what certain patterns are unique to which images. And then it comes out with a set of inputs, or sorry, a set of outputs that would be the classification for that image. So this model is basically training that this car should correspond to the output of a car. And that's basically the high-level overview. So now we're going to be zooming in and learning specifically about the convolutional, which is over here, and pooling layers, which is over here, and how they work in terms of making a convolutional neural network work. So first, let's start with the convolutional layer. Basically, this layer takes in an image, which, as we talked about earlier, is a set of pixels. So that's what this green thing is with the ones and zeros. We're just pretending that the pixel values are 1 and 0. And it drags a set of weights, which is this yellow thing, and the weights are specifically in like red. And it drags a set of weights across the image. So the set of weights is also known as a filter, and this filter is basically supposed to contain some pattern that's enclosed in this image. So for example, one of the patterns that you could be looking for is all of the edges of the image, or like certain curves or patterns basically. And in the beginning, the patterns that this filter encodes is random, so it's not going to be very accurate, but as the filter gets dragged across the image, or as the filter continues learning, the weights and the pattern that it encodes becomes more representative of the patterns in the actual image, and it'll start to match. So as the filter gets dragged across the image, the values of the filter, which is like this little 1, the 0, the 1, get multiplied by the pixel values of the image in like a matrix multiplication. And we don't really need to know the math behind it, but basically that's what happens. And then the output of the filter times the image is this convolved feature, also known as a feature map. So you repeat the process with more and more complex filters. So basically you're zooming out. So you start like very like zoomed in with like very basic curves, and then maybe you might zoom out and like look at eyes, and then at the very end, your last set of feature maps should be like representative of a face as a whole. So basically your features increase in complexity as you continue training in the model. And in terms of learning, as the model learns, the weights of this filter change so that they get better at predicting the patterns in the image. So like I said earlier, before the model has trained, the weights are going to be random and they aren't going to be very representative of any patterns in the image. But as your model trains and the weights change, eventually they will come to represent like certain patterns in the image.
I have a question. Sorry, Jui. If you do that, do you obviously have to train from, so you said you have to come to train it like a brain. So is it like you learn that this is a nose, this is an eye, and then you get more complex up to, I don't know, recognizing ethnicity? I don't know if it's possible, but can you just jump to this is the ethnic background of this person because of facial features, or do you have to teach the machine and the AI that this is a nose, this is a skin, this is this color, this is this shape, so this might be part of an ethnic, well, the ethnicity is not a good example, but because you talked about nose, you know, so do you have to train with the small features to large features to make it complex, or can you just jump onto the complex thing?
Yeah, so I'm pretty sure you always have to start with like very, I don't know what the word is, but like very zoomed in features. So like on this image, like basically you would zoom in so much that like at first you would only be looking for curves that are like oriented in a certain direction, and you would like only look at all of those curves, and then you would zoom out a little bit more and like look at maybe like half circles or so on. So you always start like really zoomed in, and then eventually you zoom out enough to look at larger patterns or more complex patterns.
Can I just add a bit? So what Zoe said is correct. There's always in a deep convolutional network, there's always a hierarchy of features that build up in complexity as you go through. But what I think you were asking is about whether you have to teach it those different levels of features. Yes. And the answer to that is no. You don't have to tell it what each different layer of complexity is about. You don't have to label and provide it answers for this is the nose and these are the eyes. You only have to give it the final answer, and it works out the intermediate steps for itself. And that is the power and the advantage of the modern deep learning methods. So, 10 years ago when I was starting my PhD, there were massive mountains of research on selecting features, on doing this by hand, on what are the right little filters that will help you to find the nose, so that you can then build the bigger categories. And the breakthrough of the deep networks that stack up the layers is that they can do that bit for themselves. Okay. You only have to tell them the answer for the final one.
Well, that's why it's prone to bias.
That's not why it's prone to bias.
Well, that's another topic.
Yeah, that's another topic.
I was wondering.
It is indirectly related, but yeah. So yes, there are features at different scales and different complexities, but you don't have to sort of dive in there and tell it each one.
Thank you.
Yeah. So basically, like building off of what Violet said in this example, suppose the features you were trying to look at were like the edges of the image. The machine learning model would start off very zoomed in, and then by the very end, the feature map should look like this, where it basically has all of the edges of the image, and you can kind of see how it resembles the actual image. So in summary, the convolutional layer takes in the image, it drags weights across the image's pixels, and then as the model trains, the weights of the filter change to match the patterns in the image, and the model will finish learning when the error is minimized. As I said earlier, that's how machine learning works, and that will happen when the filter can accurately predict the patterns in the image, or like when the patterns encoded in the filter match whatever pattern in the image it was supposed to be looking for. So we're also going to be looking at the pooling layer, which the goal of this layer is basically to simplify the image for more streamlined model training. And how it does this is it chooses one pixel value from the inputs, which in this case would be the filter maps, to represent the entire image. And this is kind of like an extra detail, but there's two main types of pooling layers, like the average and the maximum. And the average is basically self-explanatory. It just takes the average pixel value and chooses that to represent that entire image. And then the maximum just chooses the maximum pixel value and uses that to represent the entire image. And maximum pooling layer is used more commonly than average pooling layer. So those are two layers that are kind of, I would say, unique. I don't know, what do you say, Violet? I know convolutional layer would be unique to a convolutional neural network, but yeah, those are just two layers I thought might be nice to spotlight in terms of learning about the architecture of a CNN.
Well,
So
wait, can you go back to that a bit, because I got a little lost. So when we were looking at Abraham Lincoln, each pixel had a number. Then when we looked at the last thing, the convolutional layer, then it went through the matrix. So is it taking a large set of numbers and making it into a smaller set of numbers to represent that image? Is that what we're talking about when we're talking about pooling?
yeah, like it takes like a larger set of numbers and it chooses one pixel from that set of numbers to represent that entire image. And it just...
Right.
A pooling layer doesn't have to be global, so it doesn't have to be the entire image going down to one. So it can be convolutional as well. So it's a thing that also rolls along like your yellow spotlight, but in each of the yellow areas, it will take the average or pick the maximum and use that as the representation for the output. But there'll be fewer numbers coming out than went in.
Sure. So
it'll be a sort of coarser resolution, if you like,
right.
cruder, but it doesn't have to take it down to nothing.
Okay.
Yeah, I think a good example would be like over here, where there was like, I guess you could say like there was some pooling done where in a better quality version of this image, you would have actually like seen the details of his face. But because you chose like one pixel value to represent like a block of pixels in this image, it looks a bit grainier, but you can still tell like this is the image, these are the spatial relationships, but it'll just like reduce like the size of the image and therefore
so when it pulls it, it's like a summary of the data for that segment of the image.
Yeah.
Cool, thank you.
So yeah, so we just went through a lot of vocabulary and a lot of theory. So we're going to be doing a fun, I guess like competitive quiz to see how much of this we all retained and hopefully we remembered some of it. And then we'll also do a summary after in case you guys forgot.
Okay, Nila, you're on.
I'm ready.
Should I stop sharing my screen, Richard?
How do you want to do the quiz?
I think it's a Mentimeter quiz.
Okay.
No, it's we're sticking with Quizlet, Zui.
Oh, are we still Quizlet? Okay, then just give me a second then.
Okay.
That was my confusion internally, apologies.
No problem at all.
Bye, is it Patrick?
Paul.
Paul. Bye, Paul. Okay. So who among us are competitive?
Depends on the context, right?
I like being competitive at stuff I'm good at.
Try and get through this.
I'm less good. I'm like, no, I'm not that competitive. It's fine.
Whether I could surpass some of the people on this call, I'd be surprised.
I will disqualify myself.
Well,
Thank you, Violet.
No, I think Jui wants us to team up, actually, Vala. I think the pairs.
I'm thinking that.
I'm happy to go with you if that, you know.
Otherwise it is cheesy. Right, Zui, what do we need to do?
Okay, so just go to Quizlet.live in a different tab and then just enter this code.
Okay, I'm doing it on my mobile.
Me too, Quizlet. There we go.
Can you read the number out for me, Richard?
Yeah, 187
Mhm.
032.
Thank you.
Tell us your name, Richard. No, I better put a fake name actually in case.
Yeah, I
it's
was thinking. I don't want to be coming up last.
Okay, they turned all the names into animals, so nobody knows who anybody is.
Uh,
All right, here we go. So we just work away at this, shall we, Val? Zooey, sorry.
Oh, I have to create the game or start the game first. So when everybody's in, I guess.
how do we know when everyone's in?
Well, okay, let me.
A whole bunch of people coming up. I can see that. Sorry.
We're 24 on the call, so we need 24 people on there. You can also just scan the barcode, not the barcode, the quick QR code.
Yes, good thinking.
Is Violet playing too?
She is now.
Yeah, she's decided to join.
I wanted to see what it was like, what the questions look like, because I don't, otherwise everybody would be doing stuff and I have no idea what it
Vala,
what
we're
it's like.
inclusive, of course. Now,
Yeah.
if you wouldn't mind just personal messaging me a couple
Yeah.
of
I
these
should
things
put my
as
name in as Violet, shouldn't I? We should all call ourselves Violet.
a-
When I was using these for teaching, they used to have an anonymous option. That was the most popular with the class.
We're going to end up with an I'm Spartacus moment here, aren't we?
When you've done quizzes before, Richard, how many people usually join in?
Great question. Yeah, usually about 40 to 60% of people want to partake.
Okay.
So with 12, 13, we're definitely in that. Do you just want to put a quick message on the chat if you're literally just trying to load this up and need a few more seconds? Otherwise, we'll better carry on.
Oh, yeah, I've got 3 more now.
Oh, well done. Great.
Give it another minute then.
Just give it 10 seconds then. Again, just shout if you need more time.
Do you guys want the
Oh,
music?
well done, Chris. Do we want some music? Of course.
Can you guys hear it?
This quiz music, is it? Okay, Chris is in. Technology music. That'll probably fill. Okay, should we get going?
Yep.
17 players?
Should we start?
Yeah, I think so, yeah.
Okay. Let me just start the game. Does everybody know who they are? Ooh, unicorn.
Oh no, I need to check. I'm a reindeer. Yeah, very Christmassy.
Very good. Deborah Sea Turtle, very nice.
Kathy, are you good?
Oh yeah.
Here we go. Oh, Penguin's in the lead. We need to get going.
Oh shoot. I left the thing. I don't know where I am.
Yes.
Okay.
I'm taking too long though.
Yeah, me too.
Okay, here we go.
I'm the worst reindeer ever. I lost. I lost the thing. I don't know. I'm still at 0.
Wait, I thought giraffe was on 3 and now it's gone back to.
You get one wrong.
What
What happened?
What happened to giraffe?
Well, what happened to reindeer? I just can't find my. I need to go back to Quizlet. Why I can't.
Where's the links? Not that that's me or anything.
Oh.
Boxes. That's about right. Get back to this.
No, I'm on 0.
Go on, wrong. Oh, I hit the button too quickly. It turned out to be right. That's lucky, isn't it?
Can you go up? So I see the number of the quiz. I need to reload everything. No, it's fine. I go just up 187032.
Oh. So it's Giraffe in the lead again.
Oh, what a surprise!
It was Giraffe.
Sorry, did that stop the game early?
You didn't send me any answers, Violet, like you promised.
Well
hold on
done
a
to
sec.
Unicorns and Mustang.
Hold on a
for-
second. Came fourth, and I'm not on the screen. This is a terrible place to be.
Right, where's
Well,
the
you're
result?
Unicorn,
That's a
Bridget.
very hard
I'm
quiz,
Mustang.
Huey.
Mustang.
Sorry.
A lot of that stuff was really difficult.
Oh, it was just.
But I
like,
got most of
it
the
was
answers. So
vocabulary.
it was good.
So, Bridget, you came second, did you?
I was a Mustang, so wherever that came.
Have you got the leaderboard there? Or
This
we
is my
lost
first
it?
time. I think this is all I've got.
Aw.
What we learned.
Ah, okay. What we learned. Yeah, that's the important bit, obviously, not just the competition.
Yeah,
bit,
I
sorry.
should study regression. I got regression wrong.
Okay, so
Oh, that's what it comes up for me. Hey.
Regression wasn't in this one. Regression was from last time, right?
Where's Phil? Where did you come?
oh yeah, sorry guys. I think I
Second. Brilliant. Well done.
I don't know. Did we have more than one?
There's
Sorry?
many things that we didn't see in this quiz.
Yeah.
This is a quiz for your future self.
That's what I meant. There was a lot of stuff there that was outside of today's talk.
Wow. Nella, are you admitting where you came, or are you keeping it quiet?
But I'm just a lost reindeer, really, Richard. Lost reindeer here.
Do you guys want to retake the quiz after we go over like the summary of the vocab? Because I think I might have switched the two slides and that was not a good choice.
Ah, yeah, that's what
that
got
was-
me.
No, it's good to test our knowledge and then see what we learned and then.
Yeah, so I guess we can like go to the summary slide now and can you guys see my screen
Yes.
with the vocabulary quiz?
Yes.
Okay, so this is basically the summary slide and it has all the terms from the Quizlet. So I guess like just read over it. It's pretty
Screen
self-explanatory.
capture it.
Yeah. And once you guys are familiar with these, and if you want, we can do the Quizlet again.
Categorizing data into different categories. Regression, predict the outcome of a continuous qualitative variable. Okay, that's what I'm going on. But we did cover, you have covered all of those in the session, haven't you, Dewey?
So I've covered loss,
Learning rate.
neurons, classification, training, testing, and weights. But some of these things I threw in, and learning rate, I think I already said that. But some of these things like epochs and stuff I threw in because it's just like nice to know. And in the exploration that we're going to be doing after, there's like a lot of these terms that you need to be able to manipulate. So I just thought like knowing them beforehand would be good for when you're doing the exploration. So if you have any questions about like any of these terms, I can elaborate.
Did regression models on the first session, didn't we?
Yeah, that was the first one.
That was the question I got wrong as well. So.
This is our training data.
Yeah. And the quiz will be, well, yeah, I guess. But you've seen this before, so I guess it'll just be your validation data.
I'll supervise learning for sure. Cool.
Did I just hear a picture?
Yeah.
Whose camera was that?
No, I just screenshotted as well.
Oh, all right. I was going to say I took a picture of it, and I've got no advantage if everybody does that.
Okay, is everyone good?
Let's go for it.
Okay, let's do it again.
Are we doing the quiz again?
Yes. Or is that okay? You guys want to?
I'm just conscious of time, Zoe. That's all. We're on 7:30. We need to have a hard stop at 8 for us.
Oh, okay.
Yeah, let's do it again.
Then we can do the quiz super fast. Is that okay? Like, do you guys want to do the quiz, or we can also move on?
Should we try and pack some more learning in before we finish up?
Do the quiz at the end.
Yeah, we
Sure.
can come back to the quiz if we've got time at 8 o'clock. How does that sound?
Yeah, that sounds good.
It's fun.
Okay, so now we're going to move into the more hands-on, like, exploration part of the workshop. So first we're going to do an exploration of just neural networks, not convolutional neural networks, but you'll see a lot of the vocabulary that was on the prior slide kind of in action on this in this exploration. So I'll just paste the link in the chat. Okay. Okay, so this is a link, and it'll take you to this page. Everyone can still see my screen, right?
Yeah.
Okay, so it'll take you to this page where you can basically play around with like creating a neural network with no code, and you can add a bunch of neurons and see what happens. You can add more layers and see what happens. You can change the activation function. You can make the learning rate really small or really large.
Zui, we can just see your slide. Sorry, I can't see the link that you've shown. Sorry.
Can you see it now?
Posted in the chat. The link is posted in the chat. Just click on it and open it in your own window.
Yeah, I think she was just talking through the actual screen, so I just wanted to say the slide was still there.
Can everyone see it now?
I can.
Yes.
Okay. So these are the weights of the neurons you can see. You can edit the weights and see what happens. So it's basically like you can see what happens to the performance of the model, like the test loss and the training loss, as you change different parameters and hyperparameters. And then when you want to run it to see what happens, you can just press this button here and it goes through epochs. You can go through as many epochs as you want. And yeah, so it's pretty cool. And if you guys have any questions while this is going on, please feel free to unmute or put it in the chat. And then also some things that you guys can focus on while you're going through this is what happens to the loss when you make the learning rate go up or down, what happens as the epochs go up, what happens as you increase the number of hidden layers and neurons, and can you think of any possible drawbacks of increasing the hidden layers and neurons?
Okay, can you go back to the page that you were demonstrating on? And because I was just confused. Epochs I thought was the number of times I've done it, but that's just going to keep going until you press play or pause, or do?
Well, yeah, so like in this case, you've trained your model, you've trained your model on the training data 412 times so far.
Yes, but that's controlled by pressing stop or play, yes? That's
Yeah,
not the number we put in. Cool, just want to make sure that's good. All right,
But
go and have a look.
Model on your own, you would specify that number beforehand.
Ah, okay.
Does anybody want to like share their screen as they go through it?
Who's feeling confident? Phil, are you feeling confident?
I can do if you want, but
Oh, perfect.
if anyone else wants to, then
I would do, but I'm doing it on a different machine, so I wouldn't be able to do it.
No worries, no worries.
okay. Shall I see if I can do it? That one. Is that working? So I've chosen the XOR dataset with the 4 quadrants, and the first one, it was set to tan as the activation function. So I've been playing around with what difference the activation functions work first. So when you set it off, it makes this hourglass shape once it settles into it. And the the curve where it says output, how quick, it shows you how quickly the error drops. If you pick a different activation function, ReLU, so tan H is quite a soft thing. It's shaped a bit like those hourglass boundaries. ReLU is a very straight kind of function. It's either nothing or the same thing that went in. So if you try ReLU instead, you end up with much kind of straighter lines with corners in terms of which parts it decides are blue and which parts are yellow. The other thing that is interesting potentially is if you do it again with all the same settings, do you get the same result? And the answer is no. In this case, it's failed to converge altogether. So it's sort of worked out one of the boundaries, but the bottom half, it's just failed to work out altogether. If we do it again, it'll be slightly differently positioned, quite straight lines. So the starting point, which is random in all of these optimizations, will sometimes make the difference between it working, finding a solution, and not at all. And the other one I tried, which I thought would be a laugh, was sigmoid, and it failed to learn altogether. And I suspect the learning rate is much too high for sigmoid, so it might work with a smaller learning rate. But then again, no, it's not. It's learned a bit, but not enough to actually draw boundaries. There's just all sorts of fun. I'm really enjoying this. So you can try a different data set, and for that, the sigmoid might work better. Oh no, it didn't like it at all. I usually stick with ReLU. ReLU won't work so well when the boundaries are, no, it's good enough, but you can see it's still made the boundaries out of straightish lines. Whereas if you used tan, they would probably come out rounder, but I think it wants a, oh yeah, it's coming there, it's coming there. The learning rate's too small. There you go. It's made a rounder blob, but it'll probably work rather nicer with a bigger learning rate. Oh, let's do that again and go. Yeah, it gets, but the blob will be different every time. So I don't know anyone else. I enjoyed that immensely. Thank you very much, Zui.
Yeah, that was a great demonstration. Thank you, Violet. If everyone is pretty good with that, we can move on to the next part of this workshop, which is basically the non-coding project. So this is where we're creating our own convolutional neural network to classify between whatever we want. We can do license plates, we can do like cancerous versus non-cancerous moles, hot dogs versus pumpkins, chihuahuas versus blueberry muffins, or anything. So how we do that is, let me share my screen again, is we're going to be using this thing that was developed by Google. It's called Teachable Machine, and they basically take care of all of the back-end coding for you. And all you have to do is specify the hyperparameters, which are the things that affect how the model learns, but you control them. So if you go to this tiny URL, it'll take you to Google's Teachable Machine. Oops, and you can't see my screen anymore. Can you see my screen?
Yeah.
Okay, so you go here, and you basically click image project, and this is what a convolutional neural network is basically. and you can create classes.
I can't hear anything. Is it just me?
Yeah, Zoo, we've lost your sound.
Oh, can you hear me now?
Yes.
Okay. Yeah, I'm trying to spell chihuahuas right now.
I was gonna say, chihuahuas is the most difficult word to spell.
Was. I think that's right. Okay. Hopefully that is right. It doesn't spell check, so we can save my dignity. And
It is right.
you can upload a couple images of blueberries and a couple images of chihuahuas, and then but I don't have any images. Okay, so I guess I can find some images.
You've put blueberries, but was it blueberry muffins that you specifically were looking for?
Yeah, blueberry muffins, because they look alike.
Yeah, I was going to say a blueberry probably doesn't look like a chihuahua.
Okay, so you have to upload images. So I'm just downloading
How many?
images right now.
I'm doing the same. How many would you recommend?
I am lazy, so I usually just do like 4 or 5. But in a real convolutional neural network, you would have to do thousands and hundreds of thousands of images and pre-process them and like augment them based on like if your data set is, what is it called, like lopsided or not, or so on. But for this, it works pretty well still if you do 5, so I do 5.
All right, you do 5. I'm going to do 100,000. That's me.
I suspect it does do augmentation built in anyway, but
all right,
yeah.
I'll just do
Do you want to know how big my number plate data set is?
Yeah.
It's a commercial secret, but it's it's over 1 million.
That's insane. I'm doing a research project with digital subtraction and geography images for stroke detection, and I think our data set right now is like 400,000, but we still have to add in like I think 99 more patient samples, so it'll go up.
Cool.
Right, how are we doing there? I've got my 5 blueberry muffins in. I'm now.
You're doing your chihuahuas now?
Yep, doing my chihuahua. Japanese jelly-like food product. No, that's not it, is it? Chihuahua.
I'm thinking if I search for some images, then, like for example, if I type in red cars, the red cars that it finds in Google are probably going to already have been identified by possibly a convolutional neural network before we then select them and then upload them again.
Possibly, yes. Right.
I was thinking exactly the same thing.
Okay. Everybody doing okay? I've just clicked away from the Zoom, so I'm just not aware just for a second.
Well, should we watch Richard's?
Oh, what am I volunteer for?
Yeah.
Oh, yeah. We haven't trained it yet. We can watch it as you train.
Yes.
Yeah, I'll stop sharing.
You want me to share?
Yes.
Yeah.
Okay.
See if you were doing what you said you were doing.
Wow. All right. Thanks, team. It's that moral support. That was what really keeps me
I suddenly realised when I said you want to share your screen, I said, "Oh, I hope he was doing what he said he was doing."
All right. So there's blueberry muffins, and now here's chihuahuas. And yes, I know I have a lot of tabs before anybody points that out. So
At the moment, so.
okay. The beauty about having a work laptop is you can share your screen relatively comfortably, can't you, and not worry too much. All right, I am biased because I picked the ones that looked a bit like blueberry muffins in my pictures, so I make it harder. Okay, let me tuck this out of the way. Okay, now what?
Okay, so don't press train model yet. Don't. Go to advanced.
Go to advanced. Okay.
And this is where you can manipulate all the hyperparameters that we talked about earlier. So yeah, so you can basically do that however you want, and we'll watch you.
So what does the batch size do?
What do I need to put my batch size? Oh, that's the lowest already. Okay. Learning rate. That seems a little low, doesn't it, Zui?
Okay.
No?
I think it's
Well, look.
It's all right.
It's all right. Okay. That was my next guess. And then epochs, I don't really understand because.
How many times it's gonna?
Oh, how many times it runs? Okay.
It's how many times do you have to hear a poem before you've memorized it, Richard?
For me, about 100.
Okay.
So
I've
more
So
is better performance.
how many? Yeah, I've read Milton's Paradise Lost 100 times and committed it to memory about it. Okay.
And then you can press train.
All right, let's train this bad boy. Talk amongst yourselves.
I was gonna say, how do we know it's working?
It's very exciting. We're preparing the training data. At this moment, it's going, damn, you really did make the training data similar, didn't you? You picked blueberry muffins that look like chihuahuas and chihuahuas that look like blueberry muffins. All right, we're on now. We're training. We're on 0. Leave this tab open.
You put in 100 if you don't know how long each. Oh, there we go.
No, it says leave the tab open. That's not a problem for me. I've never closed a tab in my life, so I'm. Okay.
Cool. So now you can try out.
It says it wants to use my camera. All right, I trust Google. Who wouldn't?
Oh, you don't need to use the camera.
No, you don't need to use the camera. It's just to submit the test images.
Why has it put my webcam on? Let's turn that off. Oh, it's frozen. Wonderful. Right. Export the model.
So now, no, don't export it yet. So now you want to see how well it actually detects on images you've seen before. So if you go to input on, and instead of webcam, select file, and then just go find like a different picture that you didn't use of a chihuahua or a blueberry, and then you can just upload it and we'll see if it detects it or not.
Number 6.
Okay. There we go. Oh, it's got both in it. Should I find one with just a chihuahua? Okay. That's a stuffy chihuahua. Is that too much? Let's have this one.
Okay.
Is that a bad day? Should I put Imtiaz on instead? Can you see that? Can you see my files?
Yes.
All right. I think it'll figure out if Imtiaz is anyway. Moving on. Right, here we go. Okay.
Okay, so if you scroll down, you'll see like
I can't scroll down.
6% confidence. How much?
I can zoom out.
Okay, well, in the output, it should have like a 97% confidence that like it's a chihuahua.
Oh, there we go. Oh, look at that.
What does it say?
100%. Look at that.
100% confident that that's
Look at this. I've just got a private message off Violet. It says, can you send me your CV? She said she's so impressed with what's just happened. She wants me on the team.
You get yourself a job, like you.
I know. Should we test it one more time, Zoe, since we're...
Sure.
So should I have a cranberry muffin now or something? Or
Yeah, the interesting question is what happens when you give it something completely different?
What do you want? We could have...
Well, I just did a test and it worked. I did between Japanese tattoos and other tattoos, mandala tattoos, and it found the Japanese tattoo.
Oh, very impressive.
Very good. We should be having you demo this, not me.
How will it have known the difference between that you were looking for blueberries and not berry muffins?
I don't know. Well, it knew it. Well, it knows it's a muffin.
I knew it was Japanese. So that was impressive.
Hey, who? Are you talking to me or Nella?
Well, I'm talking about what Nella was saying, because it knew the difference between a Japanese tattoo and a non-Japanese tattoo.
So I trained mine to recognize the difference between people and number plates. And if you give it people, it's pretty good at being sure that it's people. And if you give it number plates, it's pretty sure that it's number plates. The interesting thing is what happens when you give it something completely different. So I've just given a picture of a car. It's 98% sure that that's a person.
Oh,
That's narrow AI.
That's narrow AI, exactly.
Anybody else want to share their output? Just a bit of fun before we move on.
And do you want to share the screen or just the audio?
Either way, yeah, just tell us or show us. Although, Zui, I'm rapidly using your time up here, aren't I?
But that's okay, because we're almost done. So,
All right.
so congratulations, everybody. If this was your first time making a neural network, then you have made your first convolutional neural network. So you can export it and print out the source code and put it on your refrigerator or something. You can bookmark the page. I don't know. You can do whatever you want. You can even like make its own web page or something so people can like search it up. I've never tried that, but yeah. So that's really cool. And now we'll move on to doing this with code instead of without code. So let me share my screen again. Okay, so now we're basically going to be making a pretty simple, like just a couple layers CNN, and we're not going to be coding it from scratch. We're going to be using TensorFlow. So so basically I'll post the links in the chat. And in this workbook, I've taken out what I had created, like the architecture I had created. So you have all the basics, but you can create the architecture yourself, and then you can run the page and see the accuracy go up because that's the performance metric we're using. And then over here is the key with like what I did with this code. So I'll post both of the links in the chat. If you have to go, then you can just look at like what I did and maybe use it as reference for your own projects. But it's like really simple, so I don't know if you want to. And if you want to stay and work through it, then this is the workbook. So that was the key, and this is the workbook. And then you can just make a copy of it, so everybody can also have it. And I can like walk through how I was thinking of doing this. So basically some background about this project, we're basically going to be detecting different objects like that you would see on the road, and the data set we're using is called the Cypher 10 data set. So you can see like there's a truck here. I saw a deer in a different image. Like if you look at like say the 10th image and you run the cell. Oh wait, I need to run this first. You can see the 10th image is like a deer and so on. So it's like images you'd find by the side of the road, and we're going to be classifying them into different categories. So these are all the libraries we need. And this is where we declare our data set. This is where we pre-process the data to make the images into squares of 255 by 255, or I think, yeah. So this is where
255 is the white level.
Yeah, that's
so white is 255. It's not the number of pixels.
Yeah. And this is like what the image looks like, and then this is where we're building the CNN. So you set the learning rate and like the dropout rate. I'm not really sure what this is. I just always set it to that, and the batch size as like whatever you want. We can also ask Violet, but I'm not really sure like what the batch size is really matters in terms of like the performance of the model.
So the batch size, what is it so far? The batch size will determine how quickly it trains and how well it trains, but in a really subtle way. So this gradient that tells you which way to jump, you have to calculate it based on the data. And if you use the entire data set to calculate the gradient, which is what you should do in theory, it would take forever. So you take a shortcut. You say, I will estimate the gradient based on just a batch of the data and then see which way that points me. And if you make that batch too small, then you're making that estimate really crude, and it will sort of jump around depending on which examples you happen to pick. And if you make it too big, then it will take forever and not fit into memory and whatever. So that's probably quite a good guess for so far.
Okay. And yeah, so this is where you basically create the feed forward network. And then this is where we're defining, or this is where we're adding the first couple of layers. So the convolutional layer, the pooling layer, and the dropout layer. And then you can add more of these layers in like whatever combination you want. So as you can see, you can add like a combination, you can repeat this again, or you can just add like 4 pooling layers in a row or whatever you want, and you can play around with it and see what that does in terms of your loss in your accuracy. And you can also see like your training accuracy go up as it trains. So that's basically how it is. And then for people who haven't used Google Colab before, if you want to run every cell in the model or in this notebook, you just press run all. And if you want to run individual cells, you press this little button here. And if you're getting errors about like stuff not being defined, it's probably because you haven't run this cell in the beginning, because that's where it defines a lot of the libraries and stuff. So make sure you do that first. So for example, if I wanted to like see what happens if I add like 2 more of these combinations, so like I add another one of these, and then I add another one of these, and then I top it off with like this thing, and then I would like see like what does that do to my accuracy as it trains, and so on. So we can like see what happens.
My son is now playing the guitar, so apologies for the background noise. And where do we see the accuracy?
So you can see it as it's training, like as it goes through the epochs, but you can also see it on a graph if you're more visual over here. So you can see it went up pretty good. Does anybody want to share what they're doing?
I was just watching you, so I have nothing to share.
Whereas I have acquired a helper and can't reach the keyboard anymore.
Aww. So cute. Is it a him or a her?
Is a boy. Is a big, scary boy.
Nilla, are you doing any of your own testing on this coding side?
I'm so sorry. I'm just still on the other one. I found it so cool that I just added other pictures. Yeah, so I'm trying to catch up on that.
No worries.
What Dean's around, Phil's around too. I mean, I know Phil's on a different machine, but I don't know if one of those two is having a play with this.
Dean, how are you getting on?
Did you say Dean?
I did.
Doing great. I'm loving it.
Is anybody trying this out at the moment though?
Zui, your accuracy was still going up, so you could try just running it for longer, more than 10 epochs. Yeah, just give it, yeah, just see how long it takes before it levels out.
Yeah, I'm pressing buttons and I'm seeing what's happening. And I understand from a programming point of view, but that's what I do, but not so much from in detail. And I sort of understand the concept because it's been pretty well described today, I think. But I think I'd have to sit down and look at it and think a lot to actually properly grok it.
Okay. That's good feedback. Thanks, Phil.
Is it possible, Zoe, to put you on the spot, is it possible for people to have a play around, and then if they've got questions to maybe be able to submit them so that the next session?
Well, how do we want to do that? Do we want to have a group for discussion after this, or should I send around an email or something? Any feedback for me on how we might do that?
I think we only have 2 minutes now, so I don't know. I have time, but I don't know if you guys want to stay up. So we might not do a Q&A now, but we could also like create like a Google form or something where you guys submit questions, or at the beginning of the next workshop, we could ask questions.
Okay, so what I'll do, so the next session, I'll just put that up in the chat. Again, we're keeping these free, at least for the time being, until Christmas. You can read all about that one. We're iterating, we're trying to make this best it can be every time, and so your feedback's helpful, and we'll do the best we can. And then the email address, but and I have access to for this, is team@mkai.org. So if you want to send questions, I can certainly CC Zui on that. Zui, you're welcome to share your details if you'd like. I can very much keep this call going. I personally, I've got to dip off it onto some other meetings, but
I can stay for about 20 minutes before I have to go.
But I don't need my Zoom for the time being. So, what do you say, Dean?
I'll stay as long as you stay.
No, okay, so maybe it's something that we can think about, and maybe just a simple, not that I don't have enough already, but a simple WhatsApp group to be able to sort of say what people tried and screenshot it and share it and maybe take learnings from that. But
and so this is basically like my ending slide. So if you guys want to follow along with like what I do from like month to month, or things I'm listening to in terms of podcasts or books I'm reading, or like new things I'm trying, you can sign up for my personal newsletter, which is monthly, by emailing me at that email address. And I also run a nonprofit where we teach workshops that teach about the intersection of AI and biology specifically, and they're pretty fun, I would say. So if you want to attend one of those, you can go to the website there. And then if you guys would like to donate, which you don't have to, I just put that there because I needed to fill out the slide, you can just email contact@aiinspire.org for more information.